welcome to the second video in this series on propensity score methods. In this video, we look first at the propensity score theorem. The propensity score theorem shows us how powerful the propensity score really is. Once we understand this theorem, a lot of the methods that I will explain in the upcoming video in the series will be much more intuitive for you. The second thing we'll look at in this video is the W-Rust estimator. If you've not heard of this yet, it combines the regression adjustment and the inverse probability weighting estimators that we looked at in the first video in this series to create something much more powerful. This is a slightly theory-heavy video, mostly mathsy, not as much application, but this will lay the ground for the upcoming videos. So I think it's a really interesting thing to understand. I do highly recommend you to first watch the first video in this series. If you haven't yet, I linked it in the description. Nevertheless, I will give a brief overview of our setup in the beginning to recap the material. Feel free to skip this part if you're familiar with my first video. Let's briefly recap. Our goal is to solve the fundamental problem of causal inference. The problem is that we only observe realized outcomes, but not potential outcomes, which makes it hard to estimate any causal effects. The problem here is selection bias. In the previous video, we looked at ways to infer an average of the potential outcomes, including those that we don't actually observe. The key to that was the selection on observables assumption, conditional on the set of covariates, the treatment status, and the potential outcomes for both non-treated and treated are independent. We could use regression adjustment and control for the covariates. The idea here was that we model the baseline differences in potential outcomes to remove the selection bias. Another method we looked at, inverse probability weighting, involved the propensity score. The propensity score is the probability of treatment conditional on covariates. The intuition here was that people with similar propensity scores have similar potential outcomes, so by weighting appropriately, we can infer the average outcome by adjusting for the probability of treatment. A hidden assumption that we've used is the assumption of common support, which states that all individuals have a positive but not certain probability of being treated. That is, the propensity score is always between 0 and 1. Alright, let's dive into the propensity score theorem. We define the propensity score as the conditional probability of treatment given the covariates xi. And since treatment is a Bernoulli random variable, this probability is also just the expectation of the treatment variable. Now the question is, what happens if instead of conditioning on xi, we condition on the propensity score? As before, we can write this conditional probability also in terms of an expectation, since treatment is still a Bernoulli random variable. Now, let's use the law of iterated expectations. The inner expectation here is conditional on xi and the propensity score. The outer expectation is conditional only on the propensity score. Now, we can see that the propensity score is just a function of the covariates. That means there is no additional information in the propensity score that isn't already entailed in the covariates. That means that we can just drop the propensity score from the inner expectation. One way you can think about this is if you had two random variables and summed them up. You have the same information if you know the value of both random variables and their sum. And if you only knew the value of both random variables, but not their sum. You could, after all, just sum up the two values that you have and get the sum yourself, even if I didn't explicitly tell you what the sum is. This is the same principle when we drop the propensity score in the inner conditional expectation. But now the wonderful thing is, this inner expectation is just by definition the propensity score. And the outer expectation is conditional on the propensity score. So what is the expectation of the propensity score conditional on the propensity score? Well, we know the propensity score, we condition on it, so this is just the propensity score. Lots of propensity scores there. But this whole thing becomes really simple then. The probability of treatment, conditional on the propensity score, is simply the propensity score itself. Now, this result might be quite intuitive, but you probably wonder why it is so important. So let's look at the consequences of that. Well, firstly, it means that the probability of treatment, conditional on the propensity score, is the same as the probability of treatment, conditional on the covariates. But secondly, this also holds for the expectation of treatment. That essentially means that we can apply our selection on observables assumption even if we only know the propensity score. Intuitively, that's because once we know the propensity score, we know the direction of selection, and that means we can remove the selection bias. And there's a wonderful third consequence. If we look at the second equal sign here, we see that the treatment status is mean independent of the covariates conditional on the propensity score. That means that the whole effect of covariates on treatment has to go through the propensity score. So in that case, it is completely sufficient if we control for the propensity score instead of all the covariates. So that means we can replace the covariates by the propensity score. You might see this and think, oh, that's great, but we have to estimate the propensity score anyway, so why does it matter? At its core, it permits us a dimensionality reduction. You might have tons of variables with a lot of variance in xi. For example, any sort of matching estimator or substratification often becomes unwieldy in high-dimensional space. The propensity score theorem tells you that you can collapse all those dimensions into a single one, the propensity score. There's another consequence, which is the so-called balancing property. Conditional on the propensity score, treatment and covariates are independent. That's the third consequence that we've seen. The useful thing about this is that you can actually test this property and see whether you have a good specification of the propensity score. In the final video of this series, I actually show you, based on an empirical example, how these things work and that they actually work, which I found fascinating. In the previous section, we looked at the maths behind the propensity score theorem. We can also represent the whole setup in terms of a directed acyclical graph. The covariates xi, being the characteristics of a person, affect the outcome directly. For example, more ambitious people likely earn more. So there's a direct arrow pointing from x towards the outcome y. But there's also a second path. The covariates also influence the propensity score, the probability of treatment, and this in turn influences treatment status. And treatment status also influences the realized outcome. After all, it picks among the potential outcomes of the person. Now, if we only regress the realized outcome on the treatment variable d, we see that this will pick up two effects. It will pick up the direct effect of treatment on outcome, that is the treatment effect, the arrow pointing from d directly towards y. But it will also pick up an indirect effect, a backdoor path, by going this second path from d to the propensity score to x to y. This way it picks up the effect of other characteristics on the realized outcome. And now we can see that there are two ways of blocking this indirect path. We can block it by controlling on xi, then the covariates pick up their own direct effect, and we can get the average treatment effect. That's a lot like omitted variable bias, where you just control for the omitted variable. But this indirect path is also blocked if we control for the propensity score. From this then, we can also see that once we control for the propensity score, the covariates x have no more effect on the treatment. All the effect goes through the propensity score. Now, we've seen how useful the propensity score can be. Now we look at the double robust estimator. The double robust estimator combines regression adjustment on the one hand and the propensity score, namely inverse propensity weighting, on the other hand. It guarantees us that if we specify the regression correctly or the propensity score correctly, then our estimator will be consistent for the average treatment effect. That's why it's called double robust. Even if one of the two estimators is wrongly specified, for example, we use the wrong functional form, then the double robust estimator will still be consistent. That means essentially you get two shots to get the process right, and you're allowed to miss one of them. That sounds almost too good to be true, right? Well, there are indeed some drawbacks, and I discuss the double robust estimator and its properties a bit more in the next two videos of the series. But for now, let's look at how double robustness actually works. Let's start with the formula. It looks a bit convoluted, but once you see how its magic works, it becomes very nice. Here, the p-hats are the propensity scores, as usual. In particular, they are our estimated propensity score. We could have done a good job at estimating them or a bad job. We look at the consequences of that. The mu-hats are the predicted outcomes for the treated and the untreated populations. For this estimator, the double robust estimator, it's quite common to estimate two regressions separately so that you fit one regression based only on the treated data and one regression based only on the untreated population. The average treatment effect is then the average difference of the fitted values. This is slightly more complicated than just regressing on a treatment dummy, but this different approach typically makes it easier to model heterogeneous causal effects which might interact with the covariates. Alright, so we've seen this complicated formula. Now let's see how the magic of the double robust estimator works. In the first step, we assume that we correctly specify the regression so that our model of mu1 really is the conditional expectation of the realized outcome for the treated, which is the potential outcome in case of treatment for the treated. Here I'll do the derivation for the treated and thus yi1, but it works the same for the untreated and yi0. Just notice that here the expectation is also conditional on treatment. Now, in the first step, we pull out everything that's a function only of xi, since here we are conditioning on xi. Mu1 is purely a function of xi, so we can move it out of the conditional expectation. That leaves us with this overall sum. Now, we know that if we multiply the treatment indicator with the realized outcome, that's the same as if we multiply it with the potential outcome when treated due to the switching equation. Thanks to our selection on observables assumption, we can pull these terms apart since they are independent, conditional on xi. Then we can collect terms. But this term inside the brackets is just 0 because we assume that we have correctly modeled the conditional expectation. That means that this whole term is 0, and what we are left with is y1. Then mu1 is the conditional expectation, conditional on treatment, and xi. And due to the switching equation, we know that the realized outcome, in this case, is the potential outcome in case of treated, because we condition on treatment being equal to 1. But then we can use the selection on observables assumption again and end up with the expectation of the treatment potential outcome conditional on xi. And we're done. Now we've shown this for the potential outcome associated with treatment. You can follow pretty much the same steps here with the second part of the formula to derive the average of the potential outcome in case of non-treated. Okay, now for the second case, we instead assume that the propensity score is correct, such that our estimate of the propensity score p hat of xi is p of xi equals to the conditional expectation of treatment conditional on xi. Again, we want to show that the term below, this one, is equal to the expected value of yi1 conditional on x. I'll go a little bit quicker because it's mostly the same steps as we've done before. Again, we start with this conditional expectation and pull everything out that's conditional on xi. Again, we end up with this term then. Switching equation means we can rewrite this as this. This is exactly what we've done before. In the next step, we apply the selection on observables assumption to separate these two terms. Finally, we collect terms again. Now we've got the expected value of dixi, both in the numerator and the denominator, so this cancels in the fraction. But once we cancel this, the mu1 hat in the numerator cancels with the mu1 hat. That's a separate term. So what we're left with is this, the expected value of yi1 conditional on being treated and xi. But due to selection observables again, this is just equal to the conditional expectation, the potential outcome of the treated, given xi. Again, here we thought that the propensity score is correct, and it doesn't matter what mu1 hat is. It can be, as before, the correct regression. It can be a mildly incorrect regression. It can be totally absurd, like some constant -2. It doesn't matter here. The double robust method assures us that as long as the propensity score is correct, it doesn't matter what our mu1 hat is, we still end up with a correct estimate. I will spend some more time on the empirical qualities of the double robust estimator in the next 2 videos, so make sure to check those out too. Right, this was a lot of theory. The most important takeaway is that the propensity score, which determines the selection, can remove the selection bias just as well as the raw covariates can. We've seen two ways in which this works. Mathematically, the propensity score summarizes all the information on treatment status that is entailed in our covariates xi. In a directed acyclical graph, on the other hand, both controlling for the propensity score and xi blocks the indirect path of treatment to outcome, so that the treatment variable only picks up the direct effect. We've also looked at doubly robust methods. There it's really useful. It combines regression adjustment and the propensity score. If at least one of them is modeled correctly, then we get a good estimate of the average treatment effect. The next video in this series will be on interesting methods for the propensity score. We will look at matching methods, additional weighting methods, and we look at the double robust estimator a bit more. I will also mention a number of refinements for the inverse propensity weighting and some quite important sensitivity exercises when you use propensity score methods. Subscribe to receive a notification to see when the next video is uploaded. Thanks for watching. If you enjoyed this video, I'd much appreciate if you gave it a like.